Hello, everybody. We are going to start our next talk. This is about a new scheduling trick that Jack and company have built out of lessons that were learned in trying to run really large-scale systems and the scheduling complexities that come with it. The main speaker will be Jack Humphries, who's a master's student with Christos out of Stanford and now working in Google with a rather large cast of characters that have gone to shape this project. We're going to play this as a pre-recorded video, so actually taking questions during the video will be hard, but we have an explicit 15-minute window at the end. And if you can't hold your questions till then, please type them in the Q&A tab that is on the right-hand side, or raise your hand and we'll try to figure out if we can answer the emergency question. So I'm going to start the video now, and Jack will be there to take questions at the end, okay? Here we go.
Hi, my name is Jack Humphries, and I'm a software engineer on the kernel scheduling team within Google Cloud. Today, I want to share with you a kernel scheduler and a framework that we implemented at Google called ghOST. ghOST is designed to support our rapidly evolving needs of data center workloads, including our production massive scale Google search program and our microsecond scale latency packet processing program. And at the end, we welcome ideas from the Netdev community about novel ways to use ghOST. So why does kernel scheduling matter? Why did Google go to the trouble of implementing a brand new kernel schedule? Well, kernel scheduling matters for three reasons. First is performance. You have classical concerns like our processes getting a fair share of CPU time. We might want to prioritize latency sensitive apps like microsecond scale key value stores over throughput oriented apps, video rendering, analytics, and so on. And far beyond that, we have a wide range of workloads and a wide range of machine architectures, unique cache hierarchies, and accelerators that we want to schedule properly to get good performance. Second, security is really important. As an example, due to the Spectre security vulnerability, we don't want to run two different customers' threads on parallel on the same physical. And lastly, system stability is important. We want to run system daemons to keep the system healthy, but at the same time, these daemons shouldn't interfere with other workloads. So given how important kernel scheduling is to us, what are the problems with existing kernel schedulers? Well, first of all, kernel programming is difficult. You have to write kernel code in low-level languages. It's hard to bug them. The development process is slow. Rebasing onto newer kernels is hard. There's a wide variety of issues. And a really important issue is that it takes a while to roll out the kernel across our fleet. And in the tail, it can take several months to roll out a kernel update on. Additionally, another problem is that we need to modify scheduling policies quickly, and this is hard to do with Linux kernel scheduling classes today. We have new classes of workloads we want to handle, so low latency user-facing workload. New hardware requires policy revamps, NUMA nodes, CCXs, AMD's architecture, hundreds of cores, all sorts of accelerators, including our very own TPUs. And the problem is just getting worse. These architectures are so diverse, and long gone are the days where we had fairly homogeneous architecture data. So we need to modify our scheduling policies to take advantage of the unique attributes of each architecture. And lastly, we need to get upgraded policies onto machines quickly. And again, doing a machine reboot makes this really hard. And lastly, Linux only offers flexibility in policy at the per CPU level. And what this means is that when you implement the scheduling policy in Linux, the policy can be whatever you want, but you can only schedule on a per CPU basis. Each CPU schedules itself. And there's periodic load balancing, but it only happens every few milliseconds. Linux doesn't support cross CPU or cross policy scheduling. And a lot of recent academic work, including Shinjuku, Shenango, and Paladin, among others, has shown the huge benefits of having a centralized model. So a centralized model has one CPU schedule all the other CPUs in the system. And this makes it really easy to implement work-conserving policies for microsecond scale workloads. When your load changes, or if an event happens on some remote CPU, you can rebalance tasks really quickly among those remote CPUs, certainly at the microsecond scale. And this is a big improvement over today where you can only rebalance the millisecond. And you can even work with models in between the two granularities between centralized per CPU. Maybe you want something per socket granularity. So this could be per NUMA node, per CCX. You have one CPU in a node, schedule all the other CPUs. And last, per CPU models make it difficult to support multiple tenants on the same machine. Think back to the security issue I mentioned a few slides ago. We don't want to run two customers at the same time on the same physical core. And it's hard to provide this guarantee properly with a per CPU model. So just to make it a little clearer how scheduling works in Linux today, I'm going to show you the per CPU model. So each column shows a different CPU. And as you can see, I split user space and kernel space with a line down the middle. And on each CPU, there's Linux code that schedules just that CPU. Each CPU maintains a run queue, and when that CPU goes idle and the scheduler wants to run something next, it initiates a context switch to the task it chose on that CPU. And so you can see those tasks are now running on CPUs 0, 1, and 2. But if you notice on the right, CPU N is idle. So even though CPUs 0 and 2, as you can see, still have runnable tasks waiting in the run queue, those tasks don't end up running on N. Maybe a few milliseconds later, tasks will be rebalanced to CPU N. But with the state of the world right now in Linux, it's not possible to build work-conserving policy for microsecond scale apps. So some recent academic work has explored moving complexity into container-like data plane operating systems. And some examples of this are Ix and Paladin and even our own Google Snap. And the way that these data planes work is they basically take all the functionality out of the host OS and they move it into this data plane context, which can run either in Ring 3 or non-root mode in the Intel case. And essentially, they hijack the machine. The data plane might use DPDK to replace the Linux networking stack with its own. It might try to get the host scheduler out of the take it out of the equation too. Like, for example, it might spawn p threads, pin each p thread to its own CPU and have those p threads spin. And then those p threads can essentially multiplex ucontexts on top, and they can pass request descriptors between themselves very quickly, by pinning and spinning. The data plane takes CFS or whatever you may be using out of the equation. And, this is a little different from how the state of the world works today in Linux. So today, without the data plane, a request arrives, goes through the NIC passes it to the host OS Linux, and then Linux passes an application level request to the app, probably through a socket. But with the data plane, if you notice, I'm switching back and forth between the two slides here. Instead, the request goes to the hardware and then to the data, and then to the application. So, this setup worked well for the very specific workload experiments that are run in those papers, Ix, Paladin, and so on. But the problem is that it's not practical to use data production cloud system. You need a unique data plane operating system for every single app and scheduling policy you want to deploy. Obviously, on our data center machines, we have a wide variety of apps and a wide variety of policies that we use. So while there are important contributions that these data planes make, we do need to put in a lot of work in order to make that research practical to use in production. And so that leads to the question, at Google and perhaps at other large cloud providers, what do we think that an ideal scheduler should have? Well, there are 5 key points that we've identified. First, it should be easy to implement policies, port them across machines. And we should be able to optimize policies for a wide variety of targets. Again, I want to call out all of the complicated and diverse topologies that we deal with. We have NUMA nodes, CCXs, mesh topologies, accelerators. And then on top of that, applications themselves have complicated topologies. We have network receive threads, execution threads, background, idle threads. And so accounting for both the machine topology and the app topology is really difficult. These architectures are no longer as homogeneous as they used to be within our data set. We want scheduling decision delegation, meaning we should be able to separate scheduling policy from scheduling mechanism. And if we run the policy independent context, that makes it easy to run the same policy without modification across different operating systems, different machines. We want composition and partitioning of scheduling policies so that we can support multiple workloads and multiple tenants with different SLOs and different performance targets on the same machine. And last, we want non-disruptive updates. And again, this is really important for us. We want to be able to deploy updating policies across our fleet without having to wait till month for kernel change to get applied. And just beyond that too, beyond deploying a production ready policy, non-disruptive updates also make it really easy to experiment when you're customizing a policy to a specific app or to a specific machine. Each time you make a change as you're experimenting, you can try out the change in a matter of seconds rather than having to recompile the kernel and redeploy it on the machine, restart your work. So our solution to this is a brand new Linux kernel scheduler that we built called ghOST. And we're excited to share ghOST with you today. So ghOST runs scheduling policies in a user space process. It has fast and flexible abstractions. It supports a wide variety of scheduling policies, from policies tailored to microsecond scale workloads, policies tailored to co-locating latency sensitive apps with batch app, multi-tenant workload, so on. And we also support policies that operate at centralized partition or per CPU granularity or anything in between. And last, upgrades are quick. Only a process restart is required. And so I'm going to show you the design of ghOST in the next few slides, but ghOST addresses all the 5 different needs that we have in a production kernel scheduler for Linux. So let me describe ghOST to you in a nutshell. First, ghOST is implemented as a Linux kernel scheduling class. It's a normal Linux kernel scheduler that scheduled kernel thread. But all scheduling policies run user space process, microkernel or exokernel-like fashion. And just to be clear, ghOST is just the scaffolding necessary to offload policies to user space. So ghOST isn't a policy itself. It's the tools necessary to build whatever policies that you want. And I show ghOST in the diagram at the bottom. So on the left, we have the kernel. On the right, we have user space components. And the user space component, the process is that red box. We call that the agent. And I'll break this whole diagram down for you on the next few slides. But basically, the user space process implements the policy. It receives notifications about key events from the kernel through messages. So these events include things like a task was created, a task was logged, it yielded, there was a CPU timer tick, so on. And then the agent runs its scheduling policy, it makes a scheduling decision, and it commits that decision to the kernel through a transaction API that we've implemented. And so I'm going to show you this in more detail now. Let's say we want to implement the CFS policy within ghOST. So I'm going to build up the architecture of ghOST and motivate it for CFS. So as we can see here, once again, we have each CPU in its own column. And then we split user space and kernel space down the middle. And in user space, we have this gold box, which represents the ghOST user space process where the policies run. And in this process, there's one thread per CPU. And these threads are referred to as agents. And agents are the ones that implement the scheduling policy. They schedule their own core. And as a result, they maintain run queues and task state, all the other things you would expect a kernel scheduler to do. Now, tasks, let's say application tasks or kernel tasks, those, the kernel generates messages about task state when an interesting event occurs, like a thread block, yield, a task was created, it died, it left the ghOST scheduling class, and so on. So the kernel generates messages about task state, and then it shares those messages with the user space process through shared memory queues. We have something in the kernel called an associations layer, and that maps a task, a message source basically, to a queue. And then we have a routing layer that maps a queue to an agent. So when a message is added to a queue, the routing layer is used to determine which agent to wake up. And just as a reminder, the agents themselves implement the schedule policy. They maintain the run queues, the task state, and so on. And on the other hand, the queues, the routing layer, the association layer, that's what determines that this is the per CPU model. As you can see, tasks running on a specific CPU have all of their messages routed to the agent on the CPU, but the agent itself is what manages the run queue and determines what to run next. And when an agent's made up its mind about what to run, it commits that scheduling decision to the kernel with a transaction. So just to make it a little bit clearer what the difference between the models are, here's an image that lays out pretty clearly what the centralized scheduling model is. So in this case, we only have one CPU that schedules all the other CPUs. And the reason why you might want this, because it's really good for really difficult microsecond scale network workloads. You have one CPU that can see all the other CPUs in the system. It's always awake, always spinning. It can do really fast microsecond scale rebalancing of tasks between CPUs versus in the per CPU model, you can only rebalance on the millisecond granular. So the global agent implements the scheduling policy. The other CPUs still have an agent, but that agent is asleep. It doesn't wake up. It doesn't do anything. And that global agent schedules all the CPUs on the machine. So as you can see here, because this is the centralized model, we only have one queue. The association layer maps all of the task messages to that queue, and that queue is mapped to the global agent. So because this is a different model, we configure our queues and our layers different. So now I mentioned that we implemented a transaction API for agents to commit their scheduling decisions to the kernel. Agents express their intent with a transaction, and that transaction can either be synchronously or asynchronously committed. Each transaction, the agent specifies of the TID it wants to schedule, along with the target CPU that task should run on. And so for the per CPU scheduling model, an agent will only ever specify its own CPU as a target, but in the centralized model or in maybe a partition model, like a per NUMA node model, the agent will specify the CPU ID of a remote one other than. And transactions have two important properties. The first is that they're atomic. So multiple agents might be making decisions. We only want one of them to be able to schedule a CPU at any given time. And furthermore, if a transaction fails, and I'll get into reasons why in a moment, we want nice state cleanup. We don't want any sort of state lingering around the kernel related to the failed transaction. And second, transactions are retractable. So a decision could become invalid as OS state changes, like maybe an agent opens a transaction to schedule a batch app, but then it realizes at the last one, oh, a latency sensitive thread runnable. Now the agent wants to schedule that latency sensitive thread instead. Well, the agent can try to retract the transaction for the batch thread, and then it can try to schedule the latency sensitive thread. And so we have three API calls. One is to create a transaction, one is to commit a transaction, and we can actually commit multiple transactions at the same time. Like if you're the global agent and you want to schedule several remote CPUs, you can do that. And in that case, instead of having to send IPI one at a time to each remote CPU, we can instead amortize the IPI overhead across transactions, the batch. And last, you can retract transactions. Again, that's something that might fail too late and the transaction is already committed and the thread has started. So now I want to talk about how we synchronize agents with the kernel. As a reminder, the kernel is the source of truth. It's our atomic store. All task state lives in the kernel. It's ephemeral. It lives between agent restarts. And many ghost scheduler interactions happen in the context where we don't synchronously invoke an agent. So we pass messages to an agent and it will deal with it at some point in the future, but not necessarily synchronously. And so how can we keep agents in sync with the kernel? Again, if you've decided to run a batch app and then latency sensitive app wakes up, we don't want to go through and actually schedule the batch app. We want to update our decision to schedule the latency sensitive app instead. And so we've implemented something called sequence numbers. Each task has a sequence number. A new message is generated about a task, like wake up or a block or something else. Sequence number is incremented and included in the message. When an agent opens a transaction and includes the most recent sequence number that it's seen in a message about the task, right, that it queued from the shared memory queue. And then if the sequence number is outdated, the transaction fails. So the agent knows at that point that it it still has some pending messages that have arrived in the meantime. It needs to go, it needs to read those messages, potentially update its scheduling decision if there's something higher priority that it wants to run, and then it can attempt the transaction. We can also co-locate policy Ghost. Again, this is a key feature for us because we run multiple workloads on the machine. We run multiple tenants on the same machine. And we want to give them different SLOs. They have different performance constraints too. And so there are a couple different ways that we've experimented with this in Ghost. First is that you can layer within an agent, just like in Linux. You can stack policies on top of each other, and the higher priority policy can run its tasks first. And then when those are all blocked, then policy 1 or policy 2, the lower priority policies can run their tasks instead. And this is just like how Linux, you have the real-time scheduling classes, CFS. Another abstraction that we've implemented is called enclaves. So an enclave is a group of CPUs. We can split CPUs up into different groups, different enclaves, and then within an enclave, all of those CPUs are scheduled in accordance with the enclave policy. And then the last thing I want to talk about is quick upgrade to fault tolerance. With Ghost, killing and restarting the agent is done in milliseconds. There's no machine reboot necessary. And in fact, while the agent process is down, Linux can continue to schedule tasks seamlessly. We can use a simple in-kernel FIFO policy that we have in place right now to just keep the apps alive, to respond to heartbeats. This is really important for network workloads. Another option is just to kick the task back to CFS. And then we recover state when the agent restarts. And then the agent continues to schedule those tasks again. But I want to emphasize the blackout is minimal, it's less than a second. And we have seamless scheduling while the agent is down. So just to recap, Ghost is the scheduling solution for large cloud providers like Google. And it hits on the 5 different points that matter to us. It's easy to implement policies and port across machines. You can optimize policies for a wide variety of targets, all the different workloads and customers that we have, all of the diverse and heterogeneous machine architectures that we have, NUMA nodes, CCXs, accelerators, mesh architecture. It supports scheduling decision delegation. Policies are cleanly separated from mechanism. They run in independent context, easy to rebase. It's easy to port across different kernels, across different machine architectures. We support composition and partitioning of policies for different workloads, different tenants. And last, we support non-disruptive update. We can upgrade the policy in a matter of milliseconds rather than having to wait till up to months for a kernel change to be applied to all the machines in our. So now I'm going to show you how Ghost performs. I'm first going to show you some microbenchmarks, and then I'm going to show you how Ghost performs on our production packet processing framework called Snap. So first, some microbenchmarks. To start, the system call overhead on our machine that we tested this on, see at the bottom, is 72 nanoseconds. So we disable meltdown mitigations for the agent process specifically because the agent process is a trusted process. The message delivery overhead, so for the kernel to send a message to an agent, is 265 nanoseconds. A local commit, so this is when an agent wants to schedule its own CPU from the time the agent opens that transaction to when the thread that it's scheduling starts to run, is 888 nanoseconds. The context switch overhead with a trivial single task kernel scheduler is 410 nanoseconds. And the same context switch overhead with CFS is 599 nanoseconds. And the point of these bottom 2 rows is to compare Ghost with other kernel schedulers. So as you can see, Ghost has slightly higher overhead, but they're still very small. And it's practical to use Ghost for production scheduling, including for microsecond scale workloads. Just a few more micro benchmarks. So on the previous slide, I showed you the local commit overhead. This is in the per CPU model when an agent wants to schedule its own CPU. What about in the centralized model where an agent wants to schedule a remote CPU? Well, look at the table at the top. I have 3 rows there. One is the committer overhead. This is the work that the global agent has to put in to create the transaction, send the IPI. That's 668 nanoseconds. On the target CPU, the CPU being scheduled, that CPU has to receive the IPI, commit the transaction, context switch. That takes about a microsecond. and the end-to-end latency is about 1 microsecond. And then, as I said, we can also do a batch transaction in order to amortize the IPI overhead across transactions. And the key point with that is that while it does take longer overall to commit transactions, we're 10 instead of 1, um, this overhead per transaction 396 nanoseconds. So that's a lot smaller than when you're just committing a single transaction to run on a remote. So Ghost still has fairly low overheads for remote scheduling. Again, this is a key this is a key feature that Ghost provides that isn't available today in Linux. And one more thing I want to call out before getting to the Snap experiment is the lines of code in Ghost. So just for comparison, CFS has 6,200 lines of code. The Ghost kernel scheduling class has about 3,800. Our user space support library for agents has 3,100. And then our Google Snap policy has 855 lines. And I want to call this out in particular. Google Snap is a production workload that operates at the microsecond scale. And as I'll show on the next couple slides, we get similar performance to what we have in production today. And we were able to support this production workload with Ghost in just 850 lines of code. And so Ghost makes it really easy to implement with policies, adapt them to certain applications, certain machine architectures, and update them in production. So now, what is Google Snap? Snap is our internal low latency packet processing framework. You can kind of think of it as something similar to eBPF. There's one main polling thread that processes network traffic. And if the network traffic bursts and it's more than what one thread can handle, then we'll spawn additional worker threads to help handle that until it goes back down. And we currently schedule Snap with Microquanta, which is a microsecond scale real-time Linux kernel scheduler. This is something that we developed in-house specifically for Snap. And then we also, for the sake of this presentation, we implemented a centralized FIFO policy in Ghost to schedule Snap, and we compare that with Snap's performance on Microquanta. And so just as a reminder, I said that we implemented a centralized FIFO policy in Ghost in order to schedule Snap. So again, there's one global agent that schedules all the other CPUs in the system. And the reason why we want a centralized model for Snap versus Microquanta, which has to operate on the per CPU basis, the centralized model accelerates network work. It's much more responsive to load changes. It has a global view of the system, and it's always spinning, so it can quickly rebalance tasks across cores, the microsecond scale rather than the millisecond scale. Highly effective for these sorts of difficult workloads. And again, a lot of recent work, Shinjuku, Shenango, Paladin, our own Snap paper, illustrate this quite clearly. And this centralized model is a key contribution that Ghost provides over what you can do with a Linux scheduler today. And so here's some numbers, and I'm going to walk you through them. So the graph at the top shows Snap running on both Ghost and Microquanta. So Microquanta is labeled as real-time in the legends. And along the x-axis, we have different latency percentiles, 50, 99, 49, 59. And the y-axis shows the latency microsecond. And we compare Ghost with Microquanta for two different packet sizes, 64 bytes, 64 kilobytes. The reason we do this is because the 64-byte workload, those packets are so small that they don't really require much work from Snap. That workload really stresses the schedule, whereas the 64 kilobyte workload requires more work from Snap, so it stresses the scheduler a little bit less. And as we can see, for all percentiles, Ghost performs similarly, if not better, than Microquanta. So even though Ghost is running user space and it has additional overhead, it still performs really well in this production workload, and it's practical to use in production. And in fact, if you look at 4 nines or 5 nines, in some cases, Ghost performs better than Microquanta. And the reason for this is because we use the centralized model in Ghost. So Ghost can rebalance tasks between CPUs really quickly, and it can outperform Microquanta in those scenarios. And I show similar experiment at the bottom. So this is the same thing, but now we co-locate Snap with Protagonist, batch workload on the same machine. So this is a slightly more difficult case for a scheduler to handle. It has more threads, it to consider more context. And again, we can see that Ghost still performs fairly similarly to microquant. So these graphs show that Ghost has reasonable overheads that don't impact end-to-end performance. And it's reasonable to deploy Ghost production and still get really good performance, if not better performance. And one more thing I want to call out is that we're interested in using Ghost to accelerate the network stack in the mix. And I'll call out NAPI integration in particular here. So as you know, NAPI improves network performance by avoiding interrupt, drop packets under high load, and it offloads the process soft IR. And so in turn, this means that overall performance is sensitive to schedule. If you schedule your soft IRQ instead of an app, a latency sensitive app could have performance issues, and vice versa for a latency sensitive network load if you schedule an app instead of a soft IRQ. And so we can use Ghost to complement NAP. So we can implement policies in Ghost really easily with a few lines of code that are informed by app information and NAPI information. And we can get better system performance overall. Just a few things that we mentioned that we want to look into are perhaps deadline scheduling, pipeline scheduling. So if you have a packet that arrives at the computer and it has to do network processing and then several stages of app processing, perhaps you can schedule that pipeline under a global SLO, better cache locality, particularly on AMD machines that have CCXs. And another thing I want to emphasize is, again, Ghost unlocks rapid prototype. So now instead of having to, every time you make a policy change, recompile a kernel, restart the machine, restart your workload, instead, you just recompile the Ghost user space process, and then you restart the scheduling process on the machine you're experimenting on, and there are no blackouts. So this makes it really easy and fast to experiment with policy. Other future work, maybe we can, move memory management into Ghost in order to reap the same benefits that Ghost provides. Reboot upgrades is one example. New policies, of course, we want to adapt policies, create new policies for our workloads and for our new machines that are entering the data center. Tighter integration with other system stacks like the networking stack, as I mentioned. Formal verification could be an interesting direction. We isolate policy from mechanism, which in turn makes it a lot easier to verify policy. You don't have to account necessarily for atomic RCU. And then EBPF extension. And this is something we've experimented with. So we can accelerate more paths in the kernel with EBPF. There are certain paths that, even though Ghost has low overheads, we don't want to context switch to user space to handle it. So some examples are like the timer tick path or the pick next task path. We can inject custom eBPF programs into the kernel to help accelerate these paths with custom logic. And we can even use eBPF to generate better debugging profile tools for Ghost. And that's more in line with how eBPF has been traditionally. So in summary, Ghost is a new Linux kernel scheduler, production ready. It runs policies, independent user space process. It has fast, flexible abstractions, supports a wide variety of policies with good performance. Upgrades are quick, only a process restart required. So thank you for listening. Ghost is open source and we encourage you to play around with it, help contribute, give us your feedback. And if you're interested, we're always looking for great kernel developers. So feel free to reach out for us about possible job opportunities. Thank you for listening, and I will be around for 15 minutes now to answer any questions.
Thank you, Jack. We have Jack and Neel on stage, and the rules are simple. If you have a question, ask it in Q&A, and we have a few, so we're going to go through them. And if you want to get the mic so that we can make it an interactive question answer session, just raise your hand. Okay. So I'm going to go through an order that it was asked. So, and I'm just going to flash it on stage so people can, Jack, you and Neel can see it and answer at will.
Okay. So, and by the way, this is my coworker Neel. He's a staff software engineer at Google on the team, and he's has responsibility over a lot of the technical direction of the project. So very happy Neel as well. There are a lot of other people involved. So okay, so I guess maybe I'll take this one and Neel can jump next. So does a transition from user to kernel and back add too much latency? How do you avoid syscall cost? Does it not matter? So yes, it does add some latency. Certain things like meltdown mitigations we turn off, and we feel comfortable doing that because this user space agent process is trusted. We're the ones who write all the code with it. So beyond that, as you saw from the Snap experiment and other experiments you can see in the paper, in terms of end-to-end results, we are very competitive with workloads get the same performance on ghOST as they get on the other kernel schedulers that don't have any user space component and that are in use today. So it's tolerable for us. And then, as I said, there are very specific things that we do want to accelerate in the kernel without going through the agent. And for that, we use custom EBPF programs. And I really want to emphasize, like we really put a lot of time into that part, important part.
Yeah, the other thing to note here is that we don't need to use system calls to schedule a task on a CPU. We have the transaction region that decouples the agent from the CPU that's doing the scheduling. So you can imagine if an agent is scheduling 256 CPUs, like on the new AMD machines, it doesn't have to do 256 system calls. All it has to do is open up 256 transactions. And then when the CPU schedule, either because of a timer interrupt or because of unscheduling IPR, they will pick up the transaction and commit it.
So it's a shared memory pipe type of model.
Yes.
Yeah. Okay. We should keep moving quickly. We have lots of questions. So let's go to the next one. What are the main? You guys can see it, right?
Yeah, I think there's actually a lot more similarities between enclaves and C groups as opposed to differences. The reason we chose, I think it was mostly momentum during development that we chose to sort of go down the enclave path. But if you look at the conceptual similarities, they're both resource allocators, and they are like, you can point processes to a particular C group or an enclave to get the scheduling policy and the scheduling constraints of that enclave or C group. So it would be fair to say that they're a lot more similar than they're different, and maybe the implementation would change in the future.
Okay, next one.
Yeah, sorry everyone. We changed the name from Locust to ghOST at the last minute. It's the official name for Google is ghOST. So if you see Locust, it's just an outdated reference. It's the intent to enable this upstream to create user space scheduler hooks, similar to how AIX exposes these today. So I don't want to speak too much of the upstream story yet. Right now, we're just releasing it open source on GitHub so that people can play around with it. I think there's still a lot of iteration that needs to be done over the API and the exact implementation, and I'm sure that there would be quite a bit of things that need to be changed before it goes upstream. But I don't want to talk too much about that story. Neel, do you have anything?
Jack, I think the question is more about intent, right? The intent is to not.
The intent is absolutely to try to push this upstream, either in this form or a form that sort of keeps the concept of having user space be able to control its own destiny with respect to scheduling. So the intent is absolutely there.
Okay. So I have a question actually, and that's sort of related to the same one, which is there an API implication to the application, or is it hidden? But don't answer this because I think there's the same question coming up later. So we'll try to save time there. So let's go with this one. Can a system be protected against rogue or malicious agent?
Yeah, let me take this one, Jack.
Okay.
So absolutely. So you can do the normal things like, okay, signing binaries and validating that the binary is doing the right thing. However, it's not just maliciousness that we need to protect against, it's just bugs. So an agent can spin on a CPU, the agent can starve tasks. The agent can do a lot of things that are detrimental to the health of the system. So the kernel is the ultimate source of truth and the arbiter of truth. So we have some things like, if the agent doesn't yield when it's supposed to yield in a particular amount of time, we are going to destroy the enclave and move the tasks back into CFS. if the agent leaves a runnable task not running or does not give it CPU, again, for a configurable amount of time, we consider that as a misbehaving agent because we do not want tasks to starve. And then again, we destroy the enclave and consider it a failure. The tasks move into CFS and life goes on. So I think we are more, it's more likely that we are going to run into programming issues than rogue or malicious agents. But yeah, the question is valid, and we have protections in the kernel to deal with that.
What is the scheduling policy for the agent in Ghost?
This ties back into the previous question.
Yeah.
The agent by default gets the highest scheduling priority unless there is another scheduling class like CFS or RT that wants to run. In that case, the agent still gets to run at a higher priority, but it gets a hint saying that it needs to yield the CPU for these other scheduling classes. And like we talked about, there is a timeout in which the agent is supposed to do this. And the intent for the timeout is for these like global scheduling policies where there is one agent doing the scheduling for all the CPUs. It gives the agent time to find another CPU and transfer its responsibilities to that CPU and then yield the CPU where CFS wants to run, for example.
Okay. So I'm going to join my question into this one. So Peter's question is, as written, why invent a new framework? Why not try to use C groups and then EBPF to sort of do the user space tweaking, which could be similar, right? You could build a EBPF interface similar to your transaction interface and then use that as your modifier agent. And my question was sort of the other side of this, right? Because there is an application implication to this as well. I can't just take a sockets app and say, oh, it now runs with user space scheduling. I need to have some other API that connects into your centralized scheduler as well.
I can take a stab at this. So we look at EBPF and Ghost not as either or, but really complementary. There's some things that Ghost can do, for example, like the global scheduling. You're spinning in a loop, you're waiting for events and you're scheduling. That's really hard for EBPF to do because you need some sort of a trigger to take an action. There's a lot of state that Ghost can share with the application that it is scheduling or a group of applications and sort of provide a SLO for, let's say, for an RPC across a group of applications and coordinate that as the request flows from one app to another. Again, we found that keeping track of that state is difficult in EBPF. Where we see EBPF as being extremely invaluable is accelerating some operation that Ghost by its design is going to be slower than the kernel. So for example, wake up latency, right? A task wakes up, completely idle system, task wakes up, and we want to get it on the right CPU as soon as possible. Because of like the messaging and the context switch overhead and just the user and kernel separation, we are always going to be slower than the kernel. And this is a prime example where we can load an EBPF program that does application-specific like select task run QF. For those who are familiar with the Linux kernel scheduler, we can do an application-specific select task run queue and get that running on the CPU ASAP. There's other BPF integrations like pick next task that we are looking at actively, whether to elide the CPU tick message because a lot of agents don't need that. So we really see EBPF and Ghost as working hand in hand as opposed to an either or approach.
And just one thing to add, maybe Neel addressed this. I was typing to people in the chat, but people have asked too, can we just do EBPF schedulers? Another good property that Ghost provides is because it's in this independent context, it allows you to handle events asynchronously, like when a task blocks or yields or something, a message is sent to user space and that can be handled asynchronously rather having to do it directly synchronously when the event happens. So it's another property that we take advantage of. And with EBPF, I I suppose you probably have to hand it.
So guys, we are out of time. The next session started a minute ago, and I think we've seen a bunch of people there for depart. So the last question was, is it deployed? I think you guys addressed that already. So we'll call this the end of the session and see you in the next one. And this was great. It's always good to see something that is deployed, running, and actually makes a material impact. Thank you.
Thanks for having us.